Okay, so now we have some space back, and we'll do a second example. And this is going to be another example in which the domain is a subset of R2, like we had down here. But I'm going to work with the level curves instead of the graph. So the graph, if I have a function, in fact, let's just write the function in here, and it's going to be a utility function. So we're going to have u of x1, x2 equal to x1 times x2, and that's going to be on the domain R2 plus. So not defining this on all of R2, but just on the non-negative pairs in R2. Let's start right off by drawing a diagram. So let's draw the diagram here. A little bit of a wavy axis here. So this is x1. This is x2. And so to draw the diagram, let's first draw the diagram, figure out the level curves at some point. So this is going to be 1 and 1. And then let's go out here to 2 and 2. And let's go out again to 3 and 3. So I've got 3 points, and of course I could also use this point down here. So the value of the function here at 1, 1 is going to be just 1, and I'm going to draw the level curve of all of the through all of the bundles. So this is a utility function. We can think of this utility function. So this is the u is playing the role of the f in our definition, and think of this as a utility function. So think of this as a consumer. It's 2 goods. Clearly, we could do the same kind of thing for more goods, but we wouldn't be able to draw the picture so well. So this is an indifference curve, right? So this is all of the bundles. And so here I'm going to write just x. So let's say we'll write x for x1, x2. So this is u of x equals 1. And then we've got here, the utility is 4 is the value of u. So let's say this is the level curve of the function u, the indifference curve, where u is equal to 4. And of course, here we have u equal to 9. So here we have the values of our function for values 1, 4, and 9 in the level curves. And so let's ask first whether this function is concave. Well, you can see that from here out to here, to here, to here, those are uniform distances. In fact, if we measure the distance, it's clearly the square root of 2 out to here, and the square root of 2 again out to here, and the square root of 2 again out to here, the length of each of these segments here. But the values are 0, and then 1, and then 4, and then 9. So if I have drawn the graph here, and then I take just the values along here in the domain, on the graph, this is going to be going up away from the domain in a convex kind of way. And so it seems pretty clear this function is not concave, and in fact it would be easy to verify that it's not concave with just what I just described here. We could let this be x, and we could let this be y, and we could take lambda equals 1/2, and we would have the line segment joining these, and this would be right in the middle, and the convex combination of the values, 9 and 1, is 5, but the value at the convex combination is 4, so the left-hand side here would be 4, and the right-hand side would be 5. Would not be not a concave function. Again, u is playing the role of f here. Let's look at another function. And this is going to be what we call a monotone transform of the function u. That's something we're going to talk about later in the course, so I'm not going to get into the details of monotone transforms today, but you've probably all seen the idea before, but it's not necessary for what we're doing here. So let's let v of x1, x2, let that be the square root of u. So this is the square root of u of x, which is the square root of x1, x2. So the values of v, I'll put them up here. The values of v, and I'll just write over here, the values of v here, 1, because the square root of 1. Square root of 4 is the value of v on here is the square root of 4. That's 2. And the value along this indifference curve, or level curve, is the square root of 9. That's 3. So now, the value of our function v at these points seems to kind of work for concavity. That is, I go a uniform distance from here to here, here to here, here to here, and the values of v go up uniformly too, from 0 to 1 to 2 to 3. And so, indeed, that's not, of course, a proof, but indeed, it turns out we can prove that the function v is concave. It's not strictly concave, but it is concave. And u is not concave, and yet they have the same exact level curves. So from the point of view of the level curves, or if you like, from the point of view of a consumer's preferences and indifference map, these two functions could equally well serve as a utility function to describe this consumer's preferences. You could say, well, wait a minute, the numbers are different from v and u, and of course they are, but we don't think a consumer actually has, for example, a utility meter somewhere embedded in his body, or he doesn't have a smartphone that's constantly telling him what is the utility level that he's getting from the different bundles that he chooses. All we're really interested in describing the consumer's preferences is the indifference map, the preferences themselves. We don't really care about the actual numbers here. The function is just a convenient analytical tool for describing the preferences. Let's write down quickly a third function, w. For this, I won't actually write in the values. That's a little trickier. So let's let this be the log of u of x. So that would be the log of x1 plus the log of x2. Well, it's the log of x1 times x2, so let's write that another step in here. It's the log of x1 times x2. Whoop. Log of x1 times x2, which is log of x1 plus the log of x2. Let's make this the natural log, if you like. I guess it doesn't make any difference for what we have here. And I won't write in the values. Of course, the log of 0, that's not even well defined, so I'd have to redefine the function as not defined here. I would still have a convex set if I delete this. And of course, the value entity bundle here would be the log of 1, which is 0. Down here, we'd get negative values for w. Up here, we'd get positive values bigger than 0 for w. The point here simply is that this function has, again, exactly the same level curves or indifference curves as this function and this function, just different numbers associated with the particular level curves. And by the way, this function we can show is not only concave, this function is actually strictly concave. This one's concave but not strictly concave. This one is not concave at all and also not convex, of course. So the functions differ in this respect, but they have the same level curves. So let's note that even though the function u is not concave, there's a certain kind of concave or convex character to the picture here with this function u. And that turns out to be an important property, an important character. And so here we have a definition of another kind of concavity and convexity that we call quasi-concave or quasi-convex. We say a function's quasi-concave if, for any 2 points in the domain, in any scalar between 0 and 1, the value at the convex combination, here it doesn't have to be greater than or equal to the convex combination of the two values. It only has to be greater than or equal to the smaller of the two values at x and y. So let's look at our situation here with the function u, which of course is again playing the role of f, and let's see how this works. So let's take 2 points in the domain. We might as well take points on these curves. And so let's take a point here. And let's take a point, let's say, over here. Let's say this is x. And let's say this is y. This is the x and y in our definition. And we want to look at the convex combinations of these 2 points in the domain. And so let's look at any convex combination. Let's look at this one here first. That looks like it's about 1/4 of the way from x to y, so lambda is about 1/4. And notice that the value of the function u at this point is larger, well, it's smaller than the value here, but it's larger than the value down here, and the value of u at x and the value of u at y, this is the smaller value. So here in the right-hand side of this definition, with u playing the role of f, the smaller of the two values, u of x and u of y, is clearly u of y. So that's 1. So on the right-hand side here, we would have 1, the minimum of u of x and u of y. And the value at the convex combination here is clearly larger. It's not even greater than or equal. It's clearly strictly larger than the value here. And we could do that for any other 2 points. We could say this is x. We could say this is y. And we could look at any convex combination of x and y in the domain. This would be x of lambda. That would be the convex combination that appears on the left-hand side of the definition. And again, here, the minimum of u of x and u of y is u of x here. U of x is the smaller value, but the value of u at the convex combination is larger than the value of u down here. Okay, and in fact, we also can talk about strict quasi-concavity and strict quasi-convexity. And again, just as with concavity and convexity, a function is strictly quasi-concave if the inequality here is strict. And so in this case, it happens that while this function is not concave or convex, it is strictly quasi-concave because this inequality is always going to be strict. If I take a point on the convex combination for 2 points like this, the value is always going to be larger. In fact, let's take another 2 points to kind of really drive that home. Let's take this as x, and let's take this as y, right? So here, I'll draw the line segment joining x and y. And now if I take any point, any convex combination of x and y, again, we can see it is the case that the value of u at the convex combination is actually strictly larger than the value at either x or y. And in this case, the minimum value on the right-hand side of u of x and u of y is actually the same. I've got u of x and u of y both on the same indifference curve or level curve. So the minimum value is either the value of x or the value of y, but any convex combination, a strict convex combination, not at x, not at y, anything on this line segment is going to have a value of u that's larger than the value at x or y. So this is actually a strictly concave function. What about these functions? This function here has the same level curves, and it seems pretty clear intuitively that this definition just involves the level curves, or if you like, the sets of things above the level curves. And so if this function's strictly quasi-concave, this actually turns out to be strictly quasi-concave as well. And so does this. They all have the same level curves. They're all strictly quasi-concave functions. Now, we've said that we could see that there's a certain convex character to this function in that the level curves themselves are sort of convex, but it's also the case that the set of bundles above an indifference curve or a level curve is a convex set for all the bundles on or above this indifference curve or level curve. All the bundles on or above this curve, convex set, same here, convex set. It turns out that that is a convenient and useful way to characterize quasi-concave and quasi-convex functions. So here we have a definition that enables us to actually work with these sets of points, vectors, or bundles for a consumer above the indifference curve or level curve. We refer to this set as the upper contour set of a particular bundle. So here I've got lots of bundles going on here, but I think that'll be okay. So let's take this bundle X and put that into the definition here and look at the upper contour set. So this says the upper contour set, which we've used capital U sub f of x. So the sub f is to indicate that it is the upper contour set for the function f. And the x indicates the bundle or the point in the domain from which we're looking at this upper contour set. And let me just say as an aside that this capital U of x and capital L of x for upper contour set and lower contour set, that's the notation I use. There is no standard uniform notation for this. Other people use this notation, but there's other kinds of notations people use. You're going to see various different notations. I actually don't recall what the notation is in Simon and Bloom's book or Mascole and Winston's book. Everybody uses something, and some people use this, some people use a different notation. This is what we use. It kind of works. U for upper, L for lower. So let's look at the upper contour set of this bundle here. It's the set of all vectors z in the domain whose value is at least as big as the value at x. So again, u is playing the role of f over here. So we want to look at all the vectors in R2 plus for which u of that vector z is at least as big as u of x. So it's all of the vectors, all the bundles on or above the level curve for x. Now if I take x to be this vector up here, this consumption bundle, now if I want to look at the upper contour set of this bundle or vector, that's going to be all of the bundles z, in fact, let's just put a z over here. It's all of the vectors or bundles z for which the u value at the bundle is at least as big as the u value here. So let's just say here, let's suppose u of z, the way I've drawn it, maybe that's around 16. Maybe it's on 4, 4 here. So, so this z would be in the upper contour set of x because its value is larger than the value at x. So that z would be in the upper contour set. So the upper contour sets for this function clearly are, intuitively, clearly are all convex sets. Well, that seems like if I have a quasi-concave function so that these line segments always do the right thing, it seems like that's pretty much the same thing as having the upper contour sets all be convex sets. And indeed, here we have a theorem that says that's the case. Notice the theorem says f is quasi-concave if and only if all its upper contour sets are convex sets. Let's forget the bottom part about quasi-convex for the moment. So it says if and only if. So again, this is a characterization theorem. This theorem gives us a characterization of quasi-concave functions in terms of upper contour sets and convex sets. The definition of quasi-concavity said nothing about convex sets. It was all about line segments and the values of the function. But this definition is couched in terms of convex sets. So it gives us a very useful, conceptually powerful, alternative definition, if you like, of quasi-concavity, of a quasi-concave function. So again, note that indeed, in fact, we've drawn a lot of line segments here, and those line segments would be good examples for showing that indeed the upper contour set for any one of these bundles actually is a convex set. So let's look at one last remark here, and that says that if we have a concave function, then it's going to be quasi-concave. So that remark tells us nothing about this function because this function is not concave. And the remark doesn't go the other way. It's not if and only if. We could have quasi-concave functions that aren't concave, and that's a prime example. We've seen this as quasi-concave, but it's not concave. But this remark does apply to each of these two functions because each of these two functions actually is concave. We didn't prove it, but each of these two functions is concave. This one's actually strictly concave. And indeed, each of them is quasi-concave because in that case, it's the same as this one. All three are quasi-concave. And finally, this one is not strictly concave, so this remark doesn't apply to this function. Again, it doesn't go both ways. This function is not strictly concave, so I can't conclude that it's strictly quasi-concave, even though it is. This function is strictly concave, which we didn't prove. We will be able to do that later on when we use derivatives and we associate derivative characteristics with concavity and quasi-concavity. So this function is strictly concave, actually, and this remark tells me that it's also strictly quasi-concave, which we already knew because we established these others were strictly quasi-concave, and they all have the same level curves. So let me see if we have any more here. No, I think that pretty much wraps things up for today's lecture. This is the idea of concave functions, convex. Oh, there's one more thing I should do, and that's simply to point out that if we had a quasi-convex function, it would look like this. So let's just do that over here. So I've got a quasi-convex function with a domain R2 or R2 plus. That's going to look like this if the function's increasing in this direction. Let's call it f. And so it's now the lower contour sets that are convex sets. And of course, I could have a convex function that looks like this. Cost functions tend to have this character. So I could have a convex function. Well, that's not quite right, actually. So suppose I have a function like this, but it actually increases in this direction. But again, the lower contour set is a convex set, So each of these two functions here has lower contour sets that are convex sets. So each of these two functions would be quasi-convex. And in fact, I've drawn them so that they're actually strictly quasi-convex, whether they're convex or not. And again, we know because they're strictly quasi-convex, they couldn't be concave, because if the function's concave, it's quasi-concave, and these are not quasi-concave. Okay, I think that wraps things up pretty well for today's lecture. That's it. See you next time.